Hi everybody, today we're going to talk about the inverse of a square matrix. So first we're going to talk about the definition of the inverse of a square matrix. So by definition, if you multiply a matrix by its inverse, you should always end up with an identity matrix. So remember, those were the matrices where you had ones going diagonal and everything else was a zero. Now, this should also work if you multiply the inverse by the original matrix. So the order here should not matter, which is rare because as we talked about with matrix multiplication, sometimes A times B is defined, but B times A is not. So it should work both ways, and you read it as A inverse. So it's really important to know that only square matrices have inverses. So if a non-square matrix will never have an inverse. That's very important. But even if it is a square matrix, that does not necessarily mean that it has an inverse. So some square matrices have inverses and they are called invertible or non-singular, but some do not and they're called singular. So the process of finding the inverse is as follows. So you're going to start by writing an augmented matrix, except it's a little bit larger than what we're used to. So on the left, you put your original matrix, and on the right, you're going to put an identity matrix that matches the dimensions of your original matrix. And then your goal is to use Gauss-Jordan to turn this left side into an identity matrix. So by the time you are done doing this, the right side of your equation will be your inverse matrix, which you can then double check by multiplying it to your matrix, and it should equal an identity matrix. All right, so let's give one of these a try. So here's our original matrix. So we're going to create our double augmented matrix. So since this is a 2 by 2, I'm going to have a 2 by 2 identity matrix on the right. So now our goal is to use Gauss-Jordan to turn this into a 0, this into a 0, and this into a 1. So I can see that I can really easily turn this into a 0 by adding row 1 and row 2 together, which will give us 0, 1, 1, 1. Okay, which is extra nice because not only did this become a 0, but this became a 1. So now our last goal is to turn that 4 into a 0. And I can do that by multiplying row 2 by -4 and adding it to row 1. So then I'll have a -4 and a +4. And the nice thing is this 0 won't change the 1 that we want to remain. So we end up with 1, 0, -3, -4. And our bottom row was already done. And remember, it's totally fine for the right side of our equation or of our matrix to be changing. It should be changing. It's becoming the inverse matrix. So now that we have an identity on the left, we have 1, 1, and then the rest are zeros. This remaining part on the right is actually our inverse. So remember, we can check this by doing a little bit of matrix multiplication. Let's try doing our original matrix times our inverse matrix. So we have 1, 4, -1, -3 times -3, -4, 1, 1. And if you multiply the first row with the first column here, we actually do get 1. If you multiply the first row with the second column, we should get 0. If you multiply the second row with the first column, we get 0. And if you multiply the second row with the second column, you get 1. So that proves that it is our inverse matrix. Now, of course, if you're being really, really thorough, we would want to check this as well, but you'll get that same exact identity. So that's how you can double check your work. All right, go ahead and pause the video and see if you can find the inverse of this matrix. All right, so go ahead and check your steps. So remember, if you didn't get this as your inverse, it's probably a small mistake somewhere in your work. So I would not recommend going through and trying to find your mistake. I would just recommend trying these exact steps and starting over completely. But your inverse matrix should be 3, 2, 1, 1. Okay, so now we're going to try doing a 3 by 3 matrix. So the setup is going to be the same. But this time on the right, we have to create a 3 by 3 identity matrix to match the dimensions of matrix A. All right, so here I see that we already have a 1. I see that we can turn these into zeros by adding them to multiples of row 1. So let's start by creating some zeros in that first column. So here I can do the opposite of row 1 plus row 2, and that should cancel these out. So this should become a 0. And then in my third row, I can do -6 times row 1 and add it to row 3. And this will turn into a 0 because -6 and +6. So remember, you do need to do this for the entire row. So this should give us 0, 0, 1, -1, -1, 1, 0, and 0, 4, -3, -6, 0, 1. Okay, so that's a pretty nice step because not only did we achieve a 0 here, but we got a 1 right next to it, which is definitely a step in the right direction. So now let's see if we can turn this term into a 0. And I see that we can do that simply by adding rows 1 and 2. So let's do that next. So when we add rows 1 and 2, we get 1, 0, -1, and then 0, 1, 0. Everything else will stay the same for that step. Okay, so now I'm looking at this and I'm going to try to turn this 4 into a 0. And I know I can do that by multiplying row 2 by -4 and adding it to row 3. So let's do that in the next step. And row 2 is going to stay the same. So here we're going to do -4 times R2 plus R3. And we should get 0, 0, 1, -2, -4, 1. Okay, so we're almost done, but I noticed that these need to become zeros. So I know that it's going to be really convenient to add them with some multiple of row 3 because row 3 has these zeros, which means it won't affect our 1s. And we don't even have to multiply it by anything because here we have -1 and +1. So I'm just going to add each of those to row 3. So I'm going to do R1 plus R3 and R2 plus R3. And I'm going to replace both of those, so we should get 1, 0, 0, -2, -3, 1, and 0, 1, 0, -3, -3, 1. And our bottom row was already fixed. So we are done. We now have our identity function or identity matrix on the left, which means the remainder on the right is our inverse matrix. So -2, -3, 1, -3, -3, 1, -2, -4, 1. And there you have it. All right, pause the video and give this problem a try. Give yourself plenty of time to work through it because this is really, really good practice and it can definitely take some getting used to. Okay, So same idea. If you didn't get the correct inverse matrix, I would start fresh from the beginning and try using these exact steps, but you should get -4, -2, 5, -2, -1, 2, and -1, 0, 1. All right, so now we're going to talk about one of the applications of inverse matrices, which is solving systems. So we already know many ways of solving systems, but we can actually do it with an inverse. So we can set up our system in a little bit of a different way. We're going to do A times X equals B, where A is just a coefficient matrix. X is a matrix of the variables, and matrix B is going to be just the constants. So if we set up an equation like this, we know that we're trying to find the variables. So if we can isolate matrix X, well, then we can find what those values are. So the idea is, if I'm trying to isolate matrix X, I need this to disappear. And I can make this disappear by multiplying both sides by the inverse of A inverse. So when I do that, this side is isolated, and this side becomes inverse of A times matrix B. So it is really important that A inverse comes first and matrix B comes second. But of course, this does require you to find the inverse of matrix A, which can be a little bit of work. So let's try this one together. So here, remember, the setup is slightly different than when we're doing Gaussian elimination. We're going to do a coefficient matrix times a variable matrix, and that's going to equal our constant matrix. So our coefficient matrix is going to look like this: 2, 3, 1, 3, 3, 1, 2, 4, 1. So notice it's just the coefficients. And then our variable matrix is going to look like this. The reason why it's a 3 by 1 is because if you use matrix multiplication here, if we multiply across this row and down this column, we end up with these three equations. So you end up with 2x plus 3y plus z, which is our first equation. Then across and down, you get 3x plus 3y equals z, and 2x plus 4y equals z. So writing it in this way will give you this, this same result, what you started with. And then that is going to equal -1, 1, and -2, which are your constants. So at this point, well, we want to solve for x. So we know that x is going to be A inverse times B. So now it's time to find A inverse. So I'd encourage you to pause the video and give this one a try. See if you can find A inverse. So pause the video. Okay, so here's that process that we just did in the last example. So here you should end up with A inverse is -1, 1, 0, -1, 0, 1, and 6, -2, -3. So now you're going to take that, and as we talked about, we're doing x equals A inverse times B. So here's A inverse, here's B, and we'll check to make sure that we can actually multiply them, which we can, and our result should be a 3 by 1 matrix. So if you do a little bit of matrix multiplication, you go across the rows and down the columns, you end up with 2, -1, -2, which of course represents x, y, and z. So write it as a coordinate, and you are done. Okay, the last thing I want to talk about is the formula for the inverse matrix of a 2 by 2 matrix. So this formula only works for a 2 by 2 matrix. And how it works is if you have a matrix A that is originally set up like this, the formula is 1 over A times D minus B times C. This is actually something special, which we'll talk about in a second. So this becomes a scalar. And then you multiply that to this new matrix. So this new matrix, you're essentially switching A and D, so you swap those two values, and C and B become negative. So you take this scalar and you multiply it into that matrix, and that will be your inverse. However, this only works, first of all, if this AD minus BC does not equal 0, because that would make it undefined. And I do want to point out this A times D minus B times C is actually something extremely important, which we're going to talk about pretty much over the next 2 or 3 days, and it's called the determinant. So we will come back to this, but it's called the determinant. It has a specific name. And remember, this only works for a 2 by 2 matrix. You don't have to use this formula. I just want you to know that it exists and it is possible. All right, so now I want to show you how to use this formula. So for part A, remember the first thing that we need to do is find the determinant, which is A times D minus B times C. So you're essentially taking this product, and subtracting them. So it becomes 3 times 2 minus negative 1 times negative 2, which is 4. So now we plug this into the formula. It's 1 over your determinant times, so we take our original matrix, we swap A and D, so times 2 and 3 here, and then we make our other values negative, or the opposite. So this negative 2 becomes a positive 2, and negative 1 becomes a positive 1. And now this is just scalar multiplication. I'm going to go in and multiply this to all 4 of my elements. So we get 1/2, 1/4, 1/2, and 3/4. And that is our inverse matrix. Now for part B, let's start by finding the determinant again. Remember, A times D minus B times C. So if we do that, it's 3 times 2 minus negative 6 times negative 1. So if you do that, it equals 0. So remember, our one requirement is that our determinant cannot equal 0, because if you go to plug it into the formula, you get something like this. So it turns out, even though this is a square matrix, this is invertible, which means it does not have an inverse. And the way we can justify is by saying that our determinant is equal to 0. All right, so why don't you go ahead and pause the video and give this last example a try. Okay, let's check our work. So we found the determinant, which in this case is 23. So we do 1 over 23 times the matrix 4, 1, negative 3, 5. These were swapped and these were made opposite. And you end up with 4 23rds, 1 23rd, negative 3 23rds, and 5 23rds, which is your inverse matrix. All right, that is all for today. Thank you for watching.